uniform circular motion, and the centripetal force. So, back in chapter 4, we'd found the centripetal acceleration looks something like v squared over the radius. If you have an object that's going around following a circular motion and it has a particular speed, v, with a particular radius for the circle r, you can find the size of the acceleration that that object experiences at any point. If we look at it more as a vertical thing, we'll mark our point, and it would be traveling with some speed, and it would be at some radius. As a result of this, we do end up with a centripetal acceleration of size v squared over r. Alright, when we are doing problems with forces, there will usually be two different directions, sometimes three different directions. In this particular problem, we would have a direction that is centripetal, a direction that is tangential, and not really easy to see here, but maybe going into the page, something that is normal. The normal and the tangential directions will usually have zero acceleration, whereas the centripetal direction will always have an acceleration that is v squared over r, or if you prefer, the omega squared times r version. Sometimes we do actually prefer the omega squared version. Alright, so let's consider a simple situation. Let's imagine that we have a nice frictionless tabletop. And we drill a hole in that tabletop. And then we set up a piece of string. And on one end of the string we have a mass. And we set that mass to move perpendicular to a particular direction so that it will trace out a circle. Right here we've got our radius r, and at the bottom we can put a hanging mass. If we think about the way this is going to work, the forces that are acting on this, oops, I meant to change color there. The forces that are acting on this mass m would have a normal force supporting it, we'd have a gravitational force, and then we'd have the tension. And as you can see, that tension points in the same direction as the centripetal acceleration. So what we'll be able to do is find a sum of forces in the centripetal direction, and it will look something like T is equal to m v squared over r. In this particular case, we can actually make use of the other direction, or the other object. And here, it's supported by a tension T, and as long as it isn't accelerating, we'd have mh times g. So some of these forces would give T minus mhg equals 0, which gives us the size of our tension force. And we can make use of that back in the original equation to figure out something about what the speed would have to be to make it go in a circle of a particular size. That's kind of the standard way this is going to work. There's a problem that's on the practice sheet that we cover in another video, where we talk about the friction acting on the ground, and we talk about a car trying to negotiate a circle. So if you have a circle and you have a car that's attempting to drive around that circle, viewed from above, it would just be, here's our car with its wheels at the corners, and it has a velocity, and it's trying to go around. We can talk about what the coefficient of friction would have to be for a particular speed, or what the maximum speed to go around a curve would be for a particular amount of friction. So if we have a friction coefficient mu sub s, and we look from above, the forces that we'd have would be normal acting upward, gravitational acting downward. So in this view, we'd be able to see the normal and the gravitational. Then we'd have our static friction force towards the middle. Viewed from above, we'd really only be able to see that static friction. But we'd be able to say that F sub s, sum of forces along the centripetal direction, would be F sub s equals mv squared over r. And of course, F sub s would be equal to the coefficient of friction mu sub s times the normal. Analyzing the rest of this, we've got normal minus mg would be equal to 0. It doesn't accelerate vertically, so we'd get our normal force is mg, We can substitute everything together, and it would look something like this. We can solve that for the maximum safe speed, and it would look like mu sub s times g times r and take the square root. So these are the way these problems work. It's pretty much the same as any other problem you've done so far. The centripetal acceleration always points directly towards the center of the circle that the object is tracing out. And that's where we're going to focus our thinking for a moment here. So the centripetal acceleration always points directly to the center of the circle our object is following. There are two cases where this can get confusing. One example is if you have something called a conical pendulum. It hangs at an angle, it has a length L, but it traces out a path like this. The centripetal acceleration does not point up the incline. That would be incorrect. The centripetal acceleration points directly towards the center of the circle it's tracing out, right at that point. It's centripetal acceleration. It is center-pointing acceleration. It will always point directly to the center. The other case that gets confusing is if you have something following a circular trajectory while on an inclined plane. So imagine you have a banked curve like you get at NASCAR tracks. When you're following that, you have a circle that you will trace out as you are going around that inclined plane. And the centripetal acceleration must point directly towards the center of that circle. It doesn't point down the inclined plane. It points purely horizontally towards the center of the circle it's tracing out. Now that does result in an interesting case, because if we think about forces that are acting on this, we'd have something like the normal, we'd have something like the gravitational, and then we have centripetal acceleration pointed towards the center. So when you've got inclined planes, normally you'd split vectors up along the parallel and perpendicular axes, but not usually if you have centripetal acceleration. In that case, it's easier to do the math if you keep horizontal and vertical. Missing an R. So in this case, I would actually suggest that if you're trying to do a problem like this, you split up along x and y, where x is your centripetal direction. Now this would be if mu is equal to 0, so a frictionless incline. If you go fast enough around a frictionless incline, you'll actually complete the circle at a particular radius without sliding up or down the incline, but you have to be at exactly the right speed. So you can analyze this and split it into components. That is a little bit tricky because you have to think about the angle of the incline and how that ends up interacting with the forces. So here, you remember how we'd normally split up gravitation based on this angle relative to the opposite of the normal? Well, we can use vertical angles to find the angle of the normal relative to the vertical, and that will let us split the normal up. So there will be an n cosine theta component minus mg equals 0, which is just our normal sum of forces. And there will be a sum of forces along the centripetal direction, where you can see there would be an n sine theta that must be equal to mv squared over r. Okay, I hope I'm catching enough of the ideas here. We aren't really working examples. This is just trying to get across definitions and such. But last thing to talk about, you'll hear me say centripetal force. The size of the centripetal force is always mv squared over r, or m omega squared times r. But real forces make this centripetal force. And in this most recent example, that would be the normal. Right up there. So be on the lookout for that. There's always going to be a sum of forces, and one of those forces, or sometimes two or more of them acting together, produce the centripetal force, which has a size of mv squared over r. Centripetal force should never be part of a free body diagram. Okay. So, I hope I've covered the right things. I'm going to stop the video there. I'll see you with the next one.